Hello student. Now we are going to discuss another topic in respiratory physiology, that is principles of gas diffusion. So here we are going to discuss how the oxygen and carbon dioxide transport occurs at the level of lungs, right? So what we are going to learn in this session, first we are going to discuss what is the meaning of respiratory unit and respiratory membrane, and then we are going to discuss the diffusion capacity of the lung. What is the formula used to calculate the diffusion capacity of the lung, that we are going to discuss. After that, we are going to discuss diffusion equilibrium of gases. So, this is one important concept where you have to understand the diffusion limited gas and perfusion limited gas. What is the concept of that, that you have to understand. And then we are going to discuss the alveolar gas equation, how to calculate the partial pressure of oxygen at alveolar level, that we are going to discuss. And then also we are going to discuss the physiological shunt at the level of lung, and at the end of the session we are going to discuss few MCQs. So this is our plan. Now let's start with the first topic, that is respiratory unit and respiratory membrane, right? Now the respiratory unit, so this concept we have already learned in the first chapter. Respiratory unit is nothing but that portion of the lung where the oxygen and carbon dioxide exchange is occurring, and we have already learned this concept that although there are different divisions in the tracheobronchial tree, but gas exchange occurs only in the exchange zone. So basically this respiratory unit is nothing but your exchange zone of the lung. Now we have already seen that exchange zone of the lung consists of respiratory bronchiole. So it consists of respiratory bronchioles, right? So the respiratory bronchioles is division number 17, 18, 19 according to Abel's classification. Then it's also consists of, so after this respiratory bronchial, respiratory bronchial, the next part is the alveolar duct. So alveolar duct is also there. So alveolar duct is division number 20, 21 and 22, okay. And after this alveolar duct, the remaining portion is nothing but the alveoli. So this is your alveolar duct, and then next part is the alveolus, and that is nothing but your division number 23. So this units is known as the respiratory unit because gas exchange is going to happen in this zone only. Why gas exchange will happen? Because we know that alveoli is the last division, that is the division number 23. It contains type 1 pneumocyte, which is the cells for gas exchange. And also I told you earlier that there are small buddings is there. Alveolar buds are also present at the level of this respiratory bronchiole and alveolar duct. That's why they can also take part in little amount of gas exchange, right? Now, during the discussion of the surfactant chapter, we have discussed that the alveoli contain a little amount of water at the inner lining. So, there will be a presence of little amount of water at the inner lining of this alveoli, and this water will give rise to surface tension, and to decrease that surface tension, we have the surfactant in the inner lining of the lung. So, the surfactant molecule will also be present here, right? Okay. So, this is the water molecule with the surfactant. Okay, got it. Now, these alveolus are lined by type 1 and type 2 pneumocyte. I told you earlier also. Type 1 and type 2 pneumocyte, according to their number, they are almost equal, 1:1 ratio. But if you look at the surface area of type 1 and type 2 pneumocyte, then most of the alveoli are under the covering of the type 1 pneumocyte only, right? So, most of the alveoli are under the covering of type 1 pneumocyte. So, according to surface area, 95% of the surface area is under the covering of type 1 pneumocyte. Now, why we are discussing this? Because we want to understand that when the oxygen or carbon dioxide, any gases wants to exchange from alveoli to capillary level or from capillary to alveolar level, what are the structure through which the gas has to pass through? Like for example, if I take example of the oxygen, so suppose the person has inhaled, you have inhaled inhale oxygen inside your alveoli, and now this oxygen has to reach up to the level of this capillary blood, right? So, the blood is coming here, the oxygen has to reach to the capillary blood. So, what are the intervening layer? What are the layer the oxygen has to cross? So, first of all, the oxygen has to cross this water layer along with the surfactant. Then it has to cross this type 1 pneumocyte, and type 1 pneumocyte means it will have their basement membrane. So, that is the next layer. And then it has to cross a interstitial tissue. So these are the interstitial tissue which is present between this alveolus and this capillary. So the interstitial tissue also has to cross this, oxygen has to cross this, and then it has to cross the endothelium of the capillary. So the endotheliums are there. In between these two endothelium there will be little gap, and oxygen has to pass through this gap only. So what are the layer through which oxygen is passing? All these layers are under the heading of respiratory membrane. So if I ask you, respiratory membrane consists of what are the structure or what layers, then your answer will be first, it has to cross the water along with the water and surfactant layer, water and surfactant layer. It has to cross the type 1 pneumocyte, type 1 pneumocyte along with its basement membrane. It has to cross this also. And the third, then it has to cross the interstitial tissue, interstitial tissue of the lung, interstitial tissue of the lung, and then it has to cross the endothelium cell, okay, endothelium cell of the capillary with its basement membrane. So all this component as a whole is known as a respiratory membrane through which gas exchange is going to happen. Now this respiratory membrane has a thickness of, this respiratory membrane has a thickness of only 0.6 micrometer. It can be as thin as of 0.2 micrometer also, but on an average, according to Guyton textbook of physiology, the membrane has a thickness of 0.6 micrometer, right? So if the carbon dioxide is also passing from this capillary blood to the alveoli, it has to cross the same membrane, that is known as the respiratory membrane, right? Now, the surface area of the total alveoli, all the alveoli, total 300 to 500 millions alveoli are there. If you calculate the surface area of all of these alveoli, I told you earlier, that is 70 to 75 meter square. So now I have to calculate that what is the amount of gas that can pass from this alveoli to the capillary blood in 1 minute. That is known as the diffusion capacity of gases. So the diffusion capacity of the gases is calculated by a law that has been written here. First of all, you try to answer one question. If I ask you, the diffusion of oxygen and carbon dioxide in the lung occurs by which process, your answer will be simple diffusion. So the gas exchange occurs at the level of lung by the process of simple diffusion. Now the simple diffusion, if I want to calculate the amount of simple diffusion, then the calculation or the rate of simple diffusion, then the rate calculation or amount of simple diffusion calculation is done by a law. Could you recall the name of that law? That is the Fick's law of simple diffusion. So according to Fick's law, if you apply the Fick's law at the level of lung alveoli, then the formula will be that diffusion of the lung, diffusion of the gases, diffusion capacity of the lung, that is D, denoted by D, is equal to delta P, that is the partial pressure difference between alveoli and capillary blood. So if you measure the partial pressure of oxygen at the level of alveoli and the partial pressure at the level of this capillary blood, then the diffusion, I mean the partial pressure difference between these two is nothing but the delta P. So I am writing here delta P is nothing but partial pressure difference, partial pressure difference between alveoli and capillary blood difference. Got it? Okay. Okay, so partial pressure difference. Then second is the A. A is the surface area of diffusion. So A is the surface area of diffusion, surface area of diffusion. And what I told you just now, that what is the total surface area of diffusion, that is approximately 70 to 75 meters square. So that is the total surface area of diffusion. And then coming the letter K. Now this K is a constant which is known as the diffusion coefficient. What is this K or diffusion coefficient? I mean coming later. But before that, look at this small d. So this small d is nothing but the thickness of the respiratory membrane, thickness of the membrane through which gas exchange is happening. Just now I told you that what is the normal thickness of the respiratory membrane? The normal thickness is 0.6 micrometer. So if the thickness is altering, suppose the thickness of the membrane is more, then what will happen to the diffusion capacity? Diffusion capacity is going to be decreased. If the delta P is increased, that is the partial pressure gradient between alveoli and capillary blood is increased, then the diffusion of the gases will increase. If the surface area is increased, then also the diffusion capacity will increase. So if I ask you that delta P or A or D, among all these three parameters, which one is the most important parameter for diffusion? The delta P is the most important parameter for diffusion. So what is delta P? Delta P is the partial pressure difference between alveoli or capillary, or maybe capillary to alveoli if you are thinking of carbon dioxide. So please remember that the delta P, that is the partial pressure difference between two compartments for oxygen, is equal to 11 millimeter of mercury. This is the average partial pressure difference between alveoli and capillary blood. And delta P for carbon dioxide gases on an average is 1 millimeter of mercury. Okay, so I'll explain this number. Okay, so look at, I told you that the delta P for oxygen. So if you calculate the partial pressure of oxygen at the level of alveoli, that is near equal to 100 millimeter of mercury, and the partial pressure of oxygen at the level of capillary blood, that is near equal to 40 millimeter of mercury. So difference of partial pressure between these two components is delta P for oxygen. So 100, 40. So it should be 60. But why I am writing 11 millimeter of mercury, you will understand a little later. So hold on. Similarly, if you look at the partial pressure of carbon dioxide at the level of capillary blood and the partial pressure of carbon dioxide at the level of lung alveoli, then that is known as the delta P or partial pressure difference for carbon dioxide. Again, the value is generally 46 is the partial pressure of carbon dioxide in the capillary and 40 is the partial pressure of carbon dioxide in the alveoli. So the difference is 6. But again, here I have written that the average partial pressure difference for carbon dioxide is only 1 millimeter of mercury, and the average partial pressure difference for oxygen is 11 millimeter of mercury. For the time being, you just remember this number. Later on, I will explain why it is 11, why it is 1. Okay. Now coming to the A, surface area of diffusion. So surface area of diffusion, it may be increased. Okay, surface area of diffusion may be increased. Suppose there is hyperinflation of the lung, hyperinflation of lung. Like for example, in case of acute asthma, there is a little hyperinflation of the lung. So if there is hyperinflation, there will be increase in surface area of the lung alveoli, and if the surface area is increased, then the diffusion capacity will also increase. But most of the cases, the important thing is that there are certain conditions where this diffusion surface area or the A decreases. So decreased surface area for diffusion is seen in many diseases. The typical example is emphysema. Because we have already explained multiple times that in emphysema, some of the alveoli get ruptured. So if there is rupture of the certain alveoli, so type 1 pneumocyte is going to be destroyed and diffusion is not going to happen. The similar thing is also seen in case of old aged lung, right? So the emphysema like scenario can also be seen in very old age lung. So that is the second example of the decreased surface area for diffusion. And obviously, if there is resection or due to some operation, some portion of the lung is cut out, then also the diffusion area, surface area will also decrease, right? So that is regarding A. And the third parameter, that is D. Okay, so D is the diffusion distance or the thickness of the membrane. Normal thickness we know, but you have to remember there are certain conditions where this thickness of the membrane increases. So increased thickness of the membrane can be seen in case of fibrosis of the lung. So that's why we know that if there is lung fibrosis, then the D or the thickness of the membrane or through which the gas exchange is occurring, the thickness will increase and diffusion capacity will be decreased. Not only that, if there is, suppose there is pulmonary edema, in case of pulmonary edema also, because of the deposition of the water in the interstitial space, the diffusion membrane thickness will be increased and the diffusion capacity is going to be decreased. Okay, so now you have understood all these three parameters, how they are going to change the diffusion capacity. Now we are coming to this K. This is a constant. I told you the name of this constant is diffusion coefficient. Okay, diffusion coefficient. Now this diffusion coefficient depends on two factors. So K is equal to S upon mW. So what is this mW and S? So S is the solubility of the gas in liquid and mW is the molecular weight of the gas. So although we are saying that the K is a constant, but this constant also depends on two things. One is the solubility of the gas and one is the molecular weight. So as you can find out here, if the solubility of the gas in liquid is more, then obviously the diffusion capacity will also be more. And if the molecular weight of the gas is lesser, then the diffusion capacity will be more because K will increase in that cases. So simple thing is that if the gas is more soluble, so more diffusion will occur. If the gas has a lighter weight or the molecular weight is lesser, then also the diffusion capacity will be increased. Now this K has a fixed value. For respiratory system, we assume that the diffusion capacity K has a value of 1. So what I am saying? We are assuming that for oxygen gas, the diffusion capacity, diffusion coefficient is 1. Okay. So we are assuming that the diffusion coefficient is, okay. So I am writing here again. So diffusion coefficient for oxygen is equal to 1. Okay. For oxygen. Get it? Okay. So, in respect to these oxygen gases, if you calculate the diffusion capacity of carbon dioxide, then it is 20.3. What is this meaning? This means that the diffusion of carbon dioxide is faster. So, carbon dioxide diffusion is faster. How much time faster than oxygen? Approximately 20 times faster than oxygen. Getting my point? So this is the meaning that although the partial pressure, okay, the surface area, the thickness of the membrane, all of these parameter can change the diffusion. But even after considering all these parameter, if you think of the diffusion coefficient, which depends on the solubility and molecular weight of the gas, so compare the oxygen and carbon dioxide, the diffusion coefficient for oxygen, if it is 1, then the diffusion coefficient for carbon dioxide will be 20. This means the carbon dioxide diffusion faster than that of the oxygen. How much faster? 20 times faster than that of the oxygen. That's why you know that in case of, suppose the one person is suffering from lung fibrosis, suppose this person is suffering from lung fibrosis and there is deposition of huge amount of fibrous tissue in the lung interstitial interstitial space. So what will happen to the diffusion thickness or the membrane thickness? The membrane thickness will be increased, and what will happen to the diffusion? Diffusion will decrease. But look at, so oxygen will not be able to diffuse through this membrane. So simple thing is that oxygen diffusion will reduce. But for the same problem, if you think of the carbon dioxide diffusion from capillary blood to alveoli, what will happen? The carbon dioxide diffusion problem will not that much. Okay, why? Because if you compare the diffusion of this oxygen and diffusion of the carbon dioxide, okay, the carbon dioxide diffusion is 20 times faster than that of the oxygen. That's why, although the oxygen will suffer that I am not able to transfer, I am not able to cross this membrane. So oxygen is suffering from diffusion problem, but carbon dioxide will not suffer that much problem because the diffusion coefficient of carbon dioxide is 20 times faster than that of the oxygen. So oxygen is suffering from diffusion problem. So there will be hypoxia at the level of capillary blood. But the carbon dioxide is not suffering from that kind of problem. So carbon dioxide will easily pass through this membrane and the carbon dioxide will be washed out from this lung. So the carbon dioxide is not going to accumulate it at the level of capillary blood. That means the hypercapnia, okay, is not going to happen in the blood. Getting my point? So for the same problem, although the person is suffering from hypoxia, but the person is not suffering from hypercapnia. And that's why we say that in most of the respiratory diseases, hypoxia is more common. Hypoxia is more common than hypercapnia. Like for example, just now I discussed that in case of lung fibrosis, the person always suffer from hypoxia in lung fibrosis, but hypercapnia is not that much common. Hypercapnia will only occur if there is problem in this ventilation, if the person is not able to wash out the carbon dioxide from the lung. Suppose there is a bronchial obstruction or suppose the ventilation is reduced, hypoventilation is occurring in the person. Then the hypercapnia is not going to happen. Otherwise, the hypercapnia is not that much common because the diffusion of carbon dioxide is 20 times faster than that of the oxygen. And why that? Because carbon dioxide diffusion coefficient is 20 times more than that of the oxygen diffusion coefficient. Got it? And now the last thing is that carbon monoxide diffusion coefficient is 0.81. That means if I compare this oxygen and carbon monoxide diffusion coefficient, then 1 upon 0.81, that means 1.23 times. That means I can understand that the oxygen diffusion is 1.2 times than that of the carbon monoxide diffusion. Getting my point? So previously we have discussed that carbon dioxide diffusion is 20 times more than that of the oxygen diffusion. Now if you compare oxygen and carbon monoxide, then oxygen diffusion is 1.23 times than that of the carbon monoxide diffusion. This information will be again utilized later on. So just remember the concept here. Got it? So now you understood two things. One is the respiratory membrane. Then you understood that what is the formula for diffusion capacity calculation and how that formula will be changed in different disease condition. Now let's understand one MCQ which will be based on the formula that we have just learned. So here the question is, if gas X is 4 times soluble, so the gas X is a 4 times soluble and 4 times dense than that of the gas Y, right? What is the ratio of the diffusion of X is to Y? So X is to Y, diffusion ratio you have to calculate. Here we are going to use the same formula, and what is that formula? We have already understood that D is equal to delta P multiplied by A multiplied by K upon small d. Got it? And every other parameter are constant in this question. So this is constant, this is constant, this is constant because it is not given in the question. So we are assuming that they are constant. So diffusion is directly proportionate to K, that is the diffusion coefficient, and K is equal to S upon molecular weight. We have already learned this. So if I calculate this question X upon Y, so gas X is 4 times soluble than that of the gas Y. So, I am putting this S value and then I have to put the molecular weight. So, it is also told that it is 4 times denser than that of the gas Y. So, root over of 4, that is the density or molecular weight. So, 4 upon root over of 4. So, 4 upon 2. So, this is 2 times. So, answer of this question will be that diffusion rate of X will be twice than that of the diffusion rate of Y, because the X gas is 4 times more soluble but 4 times more denser. Got it? So this is the question that you have to remember. It has been asked in one of the GMAR question. So this is based on the simple diffusion formula. Okay. Now we are going to understand another important concept which is known as the diffusion equilibrium of gases. I will tell you what is the meaning of that. Okay. So suppose the person is taking oxygen inside the alveoli. Okay. So oxygen is going to transfer from this alveoli to the level of capillary blood. That is very simple. Now, if I want to calculate that what is the time required for the blood to cross this alveoli or to cross this area where the capillary is in contact with the alveoli. Okay. So, what you are going to understand? So, suppose one RBC is coming here, one RBC is coming here in the capillary blood. Okay. The point where the RBC is just entering at this capillary level, suppose that is a 0 time point, and then the RBC will pass through this capillary blood and then it will exit from this alveolus region. Okay. So, now the RBC is going out of this alveolar contact zone. Suppose this is T. So, what is the time gap between this 0 to T? This we want to understand. Getting my point? So, what we are going to understand here? We are going to understand that how much time the RBC is spending in this zone. In this zone means which zone? The zone where the capillary is in contact with the alveoli, because that is the time where the gas exchange is going to happen. Because if this capillary is not in contact with the alveoli, then gas exchange is not going to happen. So, this time period from 0 to T, this time is known as the transit time of gases at the level of alveoli. So, this is known as the transit time of blood, not gases, transit time of blood. So, normally the transit time at the level of alveoli is 0.75 second. Okay. So total transit time is 0.75 second, means one RBC who is just entering inside this capillary, which is in touch with this alveoli, it is going to spend 0.75 second inside this alveolar zone, inside this alveolar touch. Okay. Then it will go out of this alveoli. Okay. So within this transit time, what is going to happen? Suppose the venous blood is coming here, the oxygen partial pressure PO2 of the venous blood is 40 millimeter of mercury. Okay. And the partial pressure of oxygen in the alveoli, normally is 100 millimeter of mercury. So look at what is going to happen. So partial pressure in the alveoli is very, very high, and the partial pressure of the venous blood oxygen is only 40. So the difference is 60 millimeter of mercury. So whenever the blood is entering in this zone where it is in contact with the alveoli, the oxygen transport is going to happen. More the oxygen is entering in the capillary blood, what will happen to the partial pressure of oxygen in the capillary blood? The partial pressure of oxygen is going to rise. Okay. So first, when the blood was entering inside this alveolar region, the partial pressure of the blood was 40 millimeter of mercury. Whenever the oxygen transport is happening from alveoli to this capillary blood, the partial pressure will increase gradually. So suppose it will first increase to 50, then it will increase to 60, then 70, 80, 90, and then it will reach to 100. Now whenever the partial pressure of oxygen at the level of capillary blood is 100, further transport of oxygen is not going to happen, because whenever the partial pressure of oxygen in the capillary blood is 100 and alveolar air is also 100, so there is no difference of partial pressure, and if there is no difference of partial pressure, delta P is equal to 0. If the delta P is equal to 0, then the diffusion is not going to happen. That is very easy to understand. So now my question is, at which point the partial pressure of capillary blood will be equal to 100? Okay. So now we want to understand that at which time point the partial pressure of the capillary blood will be equal to 100. Does it require 0.75 second whole time, does it require, or it require less time? Remember that if you think of the partial pressure of oxygen, the partial pressure of oxygen will be 100 in only 0.25 seconds. That means I am writing here the diffusion equilibrium of oxygen will reach only at 0.25 second. Means when the RBC is only at 1/3 of the total transit time. 1/3 of the total transit time. What is the total transit time? 0.75 second. And equilibrium is reaching is at 0.25 second. Means 1/3 of transit time is required for diffusion equilibrium to occur. Getting my point? So now try to imagine that whenever this fresh blood is entering at the level of this alveoli, it will take up oxygen, faster, and within 0.25 second, the diffusion equilibrium between alveoli and capillary blood is going to reach. Means after this 1/3 time point of transit time, remaining portion there is no diffusion of oxygen. Same for the carbon dioxide. I will write down here that the diffusion equilibrium for carbon dioxide, will also reach at 0.25 second only. That means if you think of the carbon dioxide diffusion, it will go on, and whenever it is reaching at 1/3 of the total transit time, then the diffusion of the carbon dioxide will be completed. After that, no further carbon dioxide transport is going to happen. So I can easily understand from here that diffusion of oxygen is occurring only during the 1/3 time of the transit time. Okay, and in the remaining time period there is no diffusion of oxygen. So if I want to calculate the average partial pressure difference between alveoli and this capillary blood, so what I am going to calculate? I am going to calculate the partial pressure difference between alveoli and capillary blood, but that is not the absolute difference, that is the average difference. So initially here it is 40, initially here it is 100. So the difference is 60. But I just told that whenever the oxygen transport is happening more and more, the partial pressure difference between this alveoli and capillary blood is going to reduce gradually. So if I want to calculate the average partial pressure difference delta P for oxygen between alveoli and capillary blood, I have to take help of the integration. So from 0 to t time point, what is the partial pressure difference? And if you calculate this, it will be 11 millimeter of mercury. And in the same way, if you calculate the delta P for carbon dioxide, okay, so again you have to take this integration, and by taking this integration, it will be 1 millimeter of mercury. Got it? So this concept is very important, that although the partial pressure difference between alveoli and capillary blood or the venous blood, if you are thinking 100 minus 40, but that is not the exact scenario, because the difference of partial pressure is constantly changing, because more and more oxygen transport is happening, the partial pressure difference is decreasing. So if you take the integration, the average partial pressure difference for oxygen is 11 and average partial pressure difference for carbon dioxide is 1 millimeter of mercury. And diffusion equilibrium is reaching in how much time point? That it is reaching within 0.25 second. So if we want to plot this concept with some graphical representation, okay, how it will looks like, okay. So now here we are going to give you the concept of diffusion limited and perfusion limited gases, but before that you require the concept of this diffusion of gases, oxygen and carbon dioxide. So I told you that what is the total time required for the gases to pass through this alveolar zone, that is a 0.75 second, and that is known as the transit time. So we are dividing this x-axis, that is 0.25, okay, then 0.5 and 0.75. So this is 0.75 is the total transit time. Now during this transit time, if we calculate the partial pressure changing of oxygen, then how the partial pressure of oxygen will change during this journey, So getting my point. So this x-axis is the time when the blood is passing through this alveolar, it is entering in one side of the alveoli and then it is going out of another side of the alveoli, okay. So this is the whole transit time. So the blood which is entering here, what is the partial pressure of that blood? The partial pressure of that blood, oxygen partial pressure is 40 millimeter of mercury. So in x-axis I am putting on point, that is 40 millimeter of mercury. And what is the target? Target is that whenever the partial pressure of oxygen is equilibrate to 100, that is the point where diffusion will be stopped, okay. So we have just understood that oxygen diffusion, okay, oxygen diffusion equilibrium reached within 0.25 second only. So this way we are going to plot this curve. Look at this curve, then you will understand what is the meaning of this, okay. Got it? So look at, so what is the meaning of this curve? This meaning is that partial pressure of oxygen, okay, was 40 millimeter of mercury, and then it is reaching to 100 millimeter of mercury within how much time period? Within 0.25 time period, that is one third of the total transit time. And in the remaining time period, there is no change in partial pressure of oxygen. That means the gas exchange or oxygen exchange is happening only during the first one third of transit time. During the remaining time, there is no transport of oxygen from alveoli to the capillary blood. So during this remaining portion, if I want to increase the oxygen diffusion, that is not possible, because there is diffusion equilibrium. The partial pressure between alveoli and capillary is same to same. So only one way is there to increase the oxygen diffusion during the remaining time period, and that is nothing but to increase the fresh flow of blood into this zone. So the blood which is already present here, that is already in equilibrium with that alveoli. So no further oxygen exchange is possible. So how I can increase the oxygen diffusion? If you increase the fresh flow of blood, or if you increase the fresh flow of venous blood, then and then only the venous blood is going to take further oxygen. So that's why this kind of diffusion of oxygen is known as perfusion limited gases. That's why the oxygen diffusion is known as the perfusion limited gas. Perfusion limited gas. Why? What is the limiting factor here? The limiting factor is that if you increase the perfusion only, then and then only you can increase the oxygen diffusion. Otherwise, no further oxygen diffusion is possible. So the oxygen diffusion is so faster that the diffusion equilibrium is reaching within 0.25 second only. So if I want to increase the diffusion is very adequate here. There is no further increase in diffusion possible. Only way to increase the diffusion is increasing the fresh blood flow. That's why the oxygen is known as the perfusion limited gases or flow limited gases. So diffusion of oxygen is flow limited type or perfusion limited type. Same kind of feature is also seen for another inert gas, that is nitrous oxide. So if you think of nitrous oxide, so initially in the venous blood, nitrous oxide partial pressure will be 0, and whenever you inhale nitrous oxide in your lung, what happens? The nitrous oxide will reach equilibrium more faster than that of the oxygen. Okay, and this is the typical curve of nitrous oxide. The diffusion equilibrium is reached within only 1/10 of the total transit time, only 1/10 of the total transit time. So this nitrous oxide and this oxygen, both of this gas is showing the similar kind of phenomena. That's why it is known as the perfusion limited gases or flow limited gases. Okay, you can increase the diffusion only by changing the flow, only by changing the perfusion, not by increasing the diffusion, because diffusion is very best. You cannot increase the further diffusion because equilibrium is reaching very fast. But now think of another gas, which is carbon monoxide. Now, whenever you inhale carbon monoxide a little bit, suppose you have inhaled carbon monoxide a little bit, the gas will easily penetrate through this barrier and it will reach at the level of blood. And within this blood, the carbon monoxide is going to react with the hemoglobin. So, carbon monoxide is going to react with the hemoglobin, because we all know that carbon monoxide has very high affinity, 250 times higher affinity for hemoglobin than oxygen. Now, whenever carbon monoxide is combining with hemoglobin, this is not going to increase the partial pressure, because this is chemical bound carbon monoxide. Carbon monoxide partial pressure is not going to change. Why? Because remember one important concept: partial pressure of gases in the blood depends on the dissolved gas, not the chemical bound gas. So whatever amount of oxygen is dissolved in the blood, that oxygen will give you the partial pressure of oxygen. Whatever amount of carbon monoxide is dissolved in the blood, that will give the partial pressure of carbon monoxide. Carbon monoxide is a gas. Whenever it enters into the capillary blood, it directly combines with hemoglobin. So that's a chemical reaction, chemical bound carbon monoxide. So chemical bound carbon monoxide means partial pressure of this blood is not going to increase. So whenever the carbon monoxide curve is plotted, how it will looks like? It will looks like completely different from the oxygen and nitrous oxide. The curve will looks like this. What is the meaning of this curve? This curve means that although the carbon monoxide is entering from alveoli to the capillary blood, but the partial pressure of carbon monoxide is not rising at all. Although the blood has traveled from one end to the other end of the alveoli. That means during this transit time also, the partial pressure of carbon monoxide is not rising at all, because what is the property of carbon monoxide? It is chemically bound with hemoglobin. So carbon monoxide partial pressure is not rising in the capillary blood. So if you give more inhalation of carbon monoxide, then carbon monoxide is easily transported to the capillary blood. Is there any problem? Answer is no, because the partial pressure of carbon monoxide is not rising here at all. So if you give more carbon monoxide inhalation, more diffusion of carbon monoxide is possible. More carbon monoxide inhalation, more carbon monoxide diffusion is possible. Means perfusion is not the limiting factor here, but the diffusion is the limiting factor. The diffusion can be easily increased if you give more inhalation of the carbon monoxide at the level of alveoli. So that's why this kind of gas is known as the diffusion limited gas. Diffusion limited gas. Okay, so the diffusion can be increased easily if you inhale more carbon monoxide in the lungs. So diffusion limited gas is carbon monoxide. Sometimes oxygen can also behave like a diffusion limited gas when the person is suffering from hypoxia. So when the person suffer from hypoxia, the oxygen curve will looks like this. So I'm writing here, this is oxygen in abnormal condition. What kind of abnormal condition? Hypoxic condition. So if you take oxygen more and more, the because the person is suffering from hypoxia, the diffusion equilibrium will not reach, although the person is reaching at the end of this transit time. So this way, this is the oxygen diffusion curve in hypoxic condition. So oxygen diffusion in hypoxic condition is also a kind of diffusion limited gas. So the bottom line is that if the diffusion equilibrium is reaching within very short time period, then that kind of gas is known as perfusion limited gas or flow limited gas. But if the diffusion equilibrium is not reaching even at the end of this transit time, then that kind of gas is known as the diffusion limited gas. Got it? So, this way you have to understand the concept of the diffusion limited and perfusion limited gas. So, diffusion limited gas is carbon monoxide and oxygen in hypoxic condition, and perfusion limited gas is normal oxygen transport and nitrous oxide or any kind of inert gas transport. Okay. So, this is the concept of diffusion equilibrium and this diffusion limited and perfusion limited gas. Now, this carbon monoxide gas is also used as an index gas for calculation of the diffusion capacity of the lung. Okay. So, just now we have discussed the diffusion limited gas and perfusion limited gas. So, this is the diagram I have taken from Guyton. So, the same thing that I have explained that has been shown here, that the partial pressure of oxygen in the alveoli is 104 millimeter of mercury or 100 millimeter mercury, and the venous blood which is entering here is 40 millimeter mercury. Then it will reach to the equilibrium in the other end. But before reaching the other end of this alveolus, okay, the diffusion equilibrium is already reached within 1/3 time period of this journey, right? So, this is explained here, and this is the curve taken from another book where the x-axis is the time period that we have already discussed. So, this is the carbon monoxide diffusion, okay, this is typically of the diffusion limited gas, and we can also find out here that the oxygen diffusion and the nitrous oxide diffusion, they are the perfusion limited gas. Okay. So, now what I was saying, that carbon monoxide gas is used for calculation of the diffusion capacity of the lung. That is why carbon monoxide is known as index gas for diffusion, index gas for diffusion calculation, diffusion calculation. Okay. So, if you use carbon monoxide gas and if you measure the diffusion capacity of the lung, then it will be 17 ml per minute per millimeter of mercury. So, carbon monoxide diffusion, how much carbon monoxide diffusion is happening through the level of lung? 17 ml carbon monoxide can diffused, okay, 17 ml per 1 minute if the partial pressure difference between alveoli and capillary blood is 1 millimeter of mercury. So, whenever you calculate the diffusion capacity of carbon monoxide, so this D is the diffusion capacity, L for diffusion capacity of the lung. DLCO means this is the diffusion capacity of the lung measured with carbon monoxide, and that is 17 ml. So, now if I convert this value into DLO2, that is the diffusion capacity of lung for oxygen. I told you that oxygen transport is how much faster than carbon monoxide transport. I told you already that K, that is the diffusion coefficient value, is 1.23 times than that of the oxygen. So, if I multiply this value of carbon monoxide 17 with 1.23, that is the oxygen diffusion is 1.23 times faster than the carbon monoxide. So, it will be approximately 21 ml per minute per millimeter of mercury. Get it? So, this value you have to remember, that if I ask you what is the amount of oxygen diffusion in the whole lung in 1 minute, your answer is 21 ml, provided you are maintaining a partial pressure difference between alveoli and capillaries 1 millimeter of mercury. But what is the partial pressure difference between alveoli and capillary blood? Average partial pressure difference for oxygen is how much? I told you that is 11 millimeter of mercury. So, if I ask you what is the total amount of oxygen diffusion in 1 minute in lung? So, DLO2 will be this 21 ml if the partial pressure difference is only 1 millimeter of mercury, but actually partial pressure difference is 11 millimeter of mercury. So, if I multiply this with 11, then it will be approximately 230 ml. So, this is the amount of oxygen transport in 1 minute through the lung. Getting my point? So, through the whole lung, both the lung, what is the total amount of oxygen that is diffused in 1 minute? That is 230 ml. How we are deducing this? First, you measure what is the DLC or diffusion capacity of carbon monoxide, because that is the index gas, that is easier to measure. Okay. Then you convert this carbon monoxide value into oxygen value by multiplying it 1.23 times. Then you know that it is the value for oxygen. It is the value for oxygen when your partial pressure gradient is 1 millimeter of mercury. So, just multiply it with 11 and you are going to get the total amount of oxygen that is diffused in your lung in 1 minute. And you know that this is the total amount of oxygen which is also consumed by the whole body tissue in 1 minute, approximately 230 to 250 ml of oxygen that is consumed by whole body tissue in 1 minute. So, that is why there is an equilibrium, there is no deficiency of oxygen at the level of tissue. So, this way if you calculate the DlCO2, diffusion capacity of carbon dioxide in the lung. So, how you are going to calculate? So, we found out what is the value for oxygen diffusion, that is 21 ml is the amount of oxygen diffusion in lung in 1 minute provided partial pressure difference is 1 millimeter of mercury. We know that the carbon dioxide transport is 20 times faster than that of the oxygen transport. So, if you just multiply this, it will be around 400 to 450 ml. So, that is why please remember that this is the amount of carbon dioxide diffusion in lung in 1 minute. So, carbon dioxide diffusion is much higher than that of the oxygen diffusion in 1 minute in your lung, because carbon dioxide transport is more faster than oxygen transport because the K diffusion coefficient is more. Got it? Okay. Now we are going to understand the alveolar gas equation. So what we are going to do here, I will first explain. So first of all, whenever you are inhaling oxygen from atmosphere, you have to understand what is the partial pressure of oxygen at the level of atmospheric air. Then whenever you inhale the oxygen inside your lung, particularly when the oxygen is going through the conducting zone of the lung, there will be certain changes at the level of this conducting zone. What are the certain changes? At the level of conducting zone, you know, there will be two things. There will be change in temperature of the atmospheric air which is entering inside your lung, and second is that there will be moisturization or there will be humidification of the air. There will be humidification of the air which is entering in your lung. So, this conducting zone of the lung is very helpful. Why? Because it is changing the atmospheric air which is entering in your lung, it is changing the temperature of that. Otherwise, if very cold air is entering inside your lung, it can causes bronchospasm. So, suppose winter season is there and very cold air is entering in your lung. So, conducting zone is going to change the temperature of the air which is entering inside your lung. Okay. So, it will convert the temperature to core body temperature. Not only that, if the air which is entering here is a very dry air, then the resistance of the dry air throughout this tracheobronchial tree is very high. So, conducting zone also causes moisturization. How the moisturization will be done? The conducting zone will add water vapor in this region. So, the oxygen whenever it is entering at the level of conducting zone, because of this moisturization, because of the addition of the water vapor, the partial pressure of oxygen will drop at the level of this conducting zone. So, suppose the partial pressure of oxygen at the level of atmosphere is 160 millimeter of mercury, it will drop at the level of this conducting zone. And when the oxygen is entering further at the level of alveoli, the partial pressure of oxygen will drop down further. Why the drop down is going to happen, we are going to explain in this session, and we are also going to derive on formula by which we can directly calculate the partial pressure of oxygen at the level of alveoli. Then the oxygen is going to be transported at the level of capillary blood. The partial pressure of oxygen is going to decrease further when the oxygen is reaching at the level of the capillary blood also. Okay. So, why that decrease in partial pressure will happen, that we are also going to understand. So, first thing is that first you understand partial pressure of oxygen in the atmospheric air. Okay. So, the atmospheric air at sea level, if I ask you what is the total pressure or what is the barometric pressure, we say PB, barometric pressure. We all know that at sea level the barometric pressure is 760 millimeter of mercury, and if you ascend into high altitude, this barometric pressure will decrease. Now, this total pressure, barometric pressure, is equal to the partial pressure of the component gases, that is the Dalton's law. So, total barometric pressure, that is 760 millimeter of mercury, that is equal to the partial pressure of component gases, that is partial pressure of nitrogen, partial pressure of oxygen, and partial pressure of carbon dioxide. Although other gases are also there, but we are ignoring them. So, Dalton's law is saying that the total pressure of a gas mixture is equal to the partial pressure of the component gases. And what are the component gases that is present here? The nitrogen is the component, major component, oxygen is another major component, and carbon dioxide is another major component. So, if I ask you, what is the composition of the atmospheric air? What is the percentage of these gases? So, remember that the composition of the atmospheric air means if you collect 100 ml of atmospheric air, in that 100 ml atmospheric air, how much percentage of nitrogen is there? We all know 79% nitrogen is there. That is the composition. How much percentage of oxygen is there within that 100 ml? Approximately 21 ml oxygen is there. And how much carbon dioxide is present in that air? That is very, very less. That is 0.04 percentage. So, this percentage is known as the composition of the atmospheric air. So, composition means what is that? Composition means that is the percentage of gases in the atmospheric air. If you calculate 100 ml, so within that 100 ml, how much ml of nitrogen? That is 79 ml. Now, based on this total barometric pressure and based on this composition, we are now going to calculate the partial pressure. So, I told you earlier that the total pressure is equal to the partial pressure of the component gases, and now we know what is the percentage of these component gases. So, it is very easy to calculate the partial pressure. So, the partial pressure, okay, partial pressure of all gases. So, if I calculate the partial pressure of nitrogen Pn2, it will be total pressure, that is 760, multiplied by percentage of nitrogen, 79 percentage. So, 79 upon 100. So, it will be approximately 600 millimeter of mercury. That is why we say that at atmospheric air, what is the partial pressure of nitrogen? That is 600 millimeter of mercury, maximum partial pressure. Then if we calculate the partial pressure of oxygen, so PO2, so the same formula I am going to use, that is the total pressure 760 multiplied by percentage of oxygen, that is 21 percentage, and it will be approximately 160 millimeter of mercury. This is very, very important to understand. So, the partial pressure of oxygen in the atmosphere, this was question in JIPMAR, and most of the students do a mistake. So, they mark 100 millimeter of mercury, but 100 millimeter of mercury partial pressure is at the level of alveoli, not at the level of atmospheric air. So, atmospheric air has a partial pressure of oxygen which is 160 millimeter of mercury. And in the same way, if you calculate the partial pressure of carbon dioxide, it will be 760 multiplied by 0.04 upon 100, and it will be approximately 0.3 millimeter of mercury. That is why we say that the partial pressure of carbon dioxide in the atmospheric air is only 0.3 millimeter of mercury. So, this is first the atmospheric air. So, what we understood? We understood what is the total barometric pressure. Total barometric pressure is equal to the partial pressure of the component gases. Component gases percentage we have seen, and then we have calculated the partial pressure of different gases. Here I tell you one thing. I told you that at the level of conducting zone, there is moisturization of the air. Moisture means water vapor. What is the partial pressure of water vapor? Remember, partial pressure of water vapor at 37-degree body temperature is 47 millimeter of mercury. This information is also required to calculate the alveolar gas equation. Okay, so this value is 47 millimeter of mercury. That is the partial pressure of water vapor at core body temperature, that is 37 millimeter of mercury. Now, with this concept, we are entering at the level of inspiratory air. So, what is inspiratory air? Whenever the air is entering at your conducting zone level. So, this is the structure of an alveolus. I told you earlier that at the level of atmosphere, PO2 is 160 millimeter of mercury. Whenever the person is inhaling this oxygen, what changes is going to happen at the level of this conducting zone? The water vapor is going to add up at the level of this conducting zone. So, water vapor is going to add up here. Now, whenever the water vapor is added up in the conducting zone, so water vapor is a kind of gas. So, earlier there was 3 major component gases in the atmospheric air: nitrogen, oxygen, carbon dioxide. Now, when the air is entering at the level of conducting zone, okay, do you think the total barometric pressure is going to change? Answer is no. Total pressure will remain same. But now this total pressure will be equal to the partial pressure of water vapor plus the partial pressure of other gases, that is nitrogen, oxygen and carbon dioxide. Got it? So this is very easy to understand. So whenever the air is entering at the level of conducting zone, now the water vapor is added up. So just imagine like this, that previously this room, there was a single room. Previously, 3 person was sharing the same room. Now the same room is shared by 4 persons. So what will happen to the partial pressure of all of this? Partial pressure of all of them is going to reduce because there is addition of the partial pressure of water. Okay. So what will happen to the partial pressure of nitrogen, oxygen, carbon dioxide? All are going to be reduced. So if I want to calculate the partial pressure of oxygen in the level of this conducting zone, how I am going to calculate? I am going to calculate like this. PB was the total pressure. Now the water vapor has been added. So I am subtracting the partial pressure of water multiplied by percentage of oxygen in the normal atmospheric gas. So if I use this formula will give you the partial pressure of oxygen at the level of conducting zone, and this value is known as the partial pressure of oxygen in the inspiratory air, PiO2. What is PiO2? PiO2 is the partial pressure of oxygen in the inspiratory air. Okay, inspiratory air oxygen partial pressure. Getting my point? So the air which you have already inhaled inside your lung, but it has not reached up to the level of your alveoli. It is only at the level of conducting zone. That air is known as the inspiratory air. So if I put the normal value of all of this, so PB normal value is 760 millimeter of mercury. pH2, I told you already that water vapor pressure is 47 millimeter of mercury at core body temperature. If your body temperature is not changing, then this 47 will remain same irrespective of the altitude, multiplied by 21 upon 100. If you simplify this, this will be equal to 149. So we take it approximation of 150 millimeter of mercury. So if I ask you what is the value of PiO2, your answer will be, sir, normal PiO2 is 149 or 150 millimeter of mercury. So now we got it. So inspiratory air oxygen means this is the oxygen partial pressure which you have inhaled inside your lung, and whenever you inhaled inside your lung, because of the moisturization of the atmospheric air, there will be change in partial pressure, there will be drop of partial pressure. And how much drop? At the level of atmosphere it was 160 millimeter of mercury. Now there is drop of partial pressure at the level of conducting zone of the lung, and how much that is? That is 140 millimeter, 149 millimeter of mercury, which is approximately 150 millimeter of mercury. Got it? This is inspiratory air partial pressure of oxygen. Now, when this oxygen is entering further at the level of alveoli, what will happen to the partial pressure of oxygen at the level of alveoli? We generally write P capital AO2. So P capital A, whenever we are putting capital A, this is alveolar oxygen partial pressure. So how to calculate the alveolar air oxygen partial pressure? P capital AO2. So again I am going to draw this same diagram. So whatever amount of oxygen is reaching at the level of this alveoli, that is basically PiO2. Now from this PiO2, oxygen will be transported at the level of this capillary blood, right? So oxygen consumption is basically happening, oxygen transport is basically happening, oxygen diffusion is basically happening. So if I want to calculate that how much oxygen is going to remain at the level of this alveolar, that is the partial pressure of alveolar oxygen. So I can write the formula like this, that the partial pressure of oxygen at the level of alveoli will be equal to PiO2. So whatever oxygen has reached at the level of alveoli minus oxygen consumption or oxygen uptake at the level of capillary blood. Why I am writing oxygen consumption? Because I earlier told you that whatever amount of oxygen is diffused at the level of lung, that amount of oxygen is going to be consumed at the level of body tissue. So PaO2 will be calculated by this formula, PiO2 minus oxygen consumption. Now, how this oxygen consumption is calculated? Oxygen consumption is calculated by taking one ratio which is known as the RQ. I hope all of you know RQ means respiratory quotient. Respiratory quotient. Okay. So RQ or respiratory quotient this is equal to RQ is equal to carbon dioxide production, carbon dioxide production upon your oxygen consumption, oxygen consumption. So if I want to calculate the oxygen consumption from this formula, I can easily calculate the oxygen consumption is equal to carbon dioxide production in the body upon your RQ, right? So I am writing this formula once again, okay? So PiO2 minus oxygen consumption is equal to carbon dioxide production in the body, carbon dioxide production in the body upon your RQ, right? Now, whatever amount of carbon dioxide is produced in your body, that is going to give you the partial pressure of carbon dioxide in the arterial blood, okay, or partial pressure of carbon dioxide in the alveoli, okay. So now I'm going to change this once again. So this is equal to PiO2 minus PaCO2, partial pressure of carbon dioxide in the alveoli upon your RQ, right. Now, what we have seen earlier that this PiO2, how it is going to be calculated? PiO2 is going to be calculated like this, okay. PiO2 is going to be calculated like this, Pb minus, I'll write once again, Pb minus PH2O multiplied by FiO2 minus PaCO2 upon RQ. Look at this formula once again. So what changes I have made here? I have changes this PiO2. I have changes that PiO2, that is the inspiratory oxygen partial pressure, by putting Pb, that is the barometric pressure, minus PaH2O, that is water vapor pressure, multiplied by FiO2. FiO2 is the fraction of oxygen in the inspiratory air. I am going back here. So here I have calculated the same thing, PiO2, that is Pb minus PH2 multiplied by 21 upon 100. What is this 21 upon 100? This is the percentage of oxygen in the inspiratory air, or the fraction of oxygen in the inspiratory air. So this 21 upon 100, this fraction, this is nothing but known as FiO2, that is a fraction of oxygen in the inspiratory air. And we all know what is FiO2. Normal value of FiO2 is 21%. So please remember, if I ask you FiO2, what is the value? Your answer is 21%. And if I ask you FeO2, then what is the value? FeO2 is the fraction of oxygen in the expiratory air. So the air which is entering in your lung, that contain 21% oxygen, but the air which is going out of the lung, that contains 16% of the oxygen. That's why there was an MCQ in anesthesia, that if you give mouth to mouth respiration, means your expiratory air is the inspiratory air for the other person, how much oxygen is delivered in that condition? That is 16%. Got it? So now you look at the formula. So the whole formula, that is the PaO2, partial pressure of oxygen in the alveolar gas, partial pressure of oxygen in the alveolar gas, is equal to Pb minus PH2O multiplied by FiO2 minus PaCO2, partial pressure of carbon dioxide in the alveoli, upon your RQ. So now I am going to put the normal value of all of these parameters. So this is 760 minus 47 multiplied by 21 upon 100 minus PaCO2, partial pressure of carbon dioxide in the alveoli, is generally 40, and respiratory quotient is generally 0.8 for an average balanced diet. But we all know that RQ for the pure carbohydrate diet is 1 and RQ for the fat diet is 0.7, but we are taking here 0.8 because that is the average RQ for an balanced diet. Okay, so now if you simplify this, it will be approximately 104 millimeter of mercury, and we take it as a normal exact value of 100 millimeter of mercury. So that's why we say that the partial pressure of oxygen at the level of alveoli is 100 millimeter of mercury. So 100 to 104 millimeter of mercury is the normal partial pressure of oxygen at the level of alveolar gas. Got it? So we have understood that partial pressure of oxygen at the atmospheric air is 160 millimeter of mercury. When that oxygen is entering at the level of conducting zone, partial pressure of oxygen is falling to 149 or 150 millimeter of mercury. When that oxygen is reaching at the level of alveoli, the value is further reduced to 100 millimeter of mercury. Now, when this oxygen is transported at the level of capillary blood, the partial pressure should be 100, because just now we have understood that there is a concept which is known as the diffusion equilibrium. But if you look at the partial pressure of oxygen at the arterial blood, that is P small aO2, partial pressure of oxygen in the arterial blood, then the value is 95 to 98 millimeter of mercury. So, why there is further drop of pressure at the level of arterial blood? And to understand this concept, you have to understand what is physiological shunt. So, try to understand that. Okay. So, just now we have understood that the partial pressure of oxygen at the level of alveoli is 100 millimeter of mercury. So, the capillary blood partial pressure must has to be 100. Okay. So, the capillary blood partial pressure is also 100 millimeter of mercury. Now, when this capillary blood is saturated to 100 millimeter mercury pressure, it is going to deliver at the level of arterial blood. It is going to deliver at the level of arterial blood. That is simple. So, arterial blood partial pressure should be around 100, but that is not. Why that is not? Because look at here. When this pulmonary capillary is delivering blood at the level of this pulmonary vein, at this junction, there is drainage of bronchial vein. So, the bronchial vein is draining the deoxygenated blood at the end of the pulmonary capillary. So, what I am saying? So, at the end of the pulmonary capillary, the partial pressure of oxygen is 100 millimeter of mercury. Okay, same to same with that of the alveolus. But after that, some deoxygenated blood is reaching from this bronchial vein, and this bronchial vein is draining this deoxygenated blood at the end of the pulmonary capillary. So, what will happen? Whenever there is mixture of this pure oxygenated blood with that of the venous blood which is coming through this, which is that of the venous blood which is coming through this bronchial vein, what will happen? The partial pressure of oxygen will decrease. Okay, but look at the total amount of blood which is flowing through this bronchial vein is only 2% of the total cardiac output of our body. So, very small amount of blood is coming through this bronchial vein. Could you correlate with this bronchial vein? I told you that lung has a dual blood supply. One is bronchial artery. Okay. So, the bronchial artery will give the pure oxygenated blood to the conducting zone up to the level of the respiratory zone, and then it will be converted into bronchial vein. So, bronchial vein is the venous blood. Where this bronchial vein is supposed to drain, it's supposed to drain in the venous side, but that is not happening here. The bronchial vein is draining is deoxygenated blood at the level of end of the pulmonary capillary, that is mixture of the pure oxygenated blood with that of the venous blood, and this kind of mixture is known as the shunt. So, this shunt, there is mixture of venous blood with the pure oxygenated blood, but it is not pathological shunt. This is happening in all lungs. So, this is a physiological phenomena, but the amount of this bronchial venous blood is only 2% of the total cardiac output. That is why there will be certainly dropping of the partial pressure of oxygen in the arterial blood, but that drop will not be significant. That is why although it should be 100, but the partial pressure of oxygen in the arterial blood drop to 95 to 98 millimeter of mercury. Got it? So, now we look at the physiological shunt picture in the books. So, as you can see here, the lung has dual blood supply. One is this pulmonary artery which is containing the venous blood from the right ventricle, and this is the bronchial artery which is the branch of the thoracic aorta that I have already told you. Now, this bronchial artery is supplying this conducting zone and the upper part of the respiratory tract, and then it is converting into the bronchial vein, and where this bronchial vein is draining, the bronchial vein is draining at the end of this pulmonary capillary. So, this bronchial vein, so this is shunt. This shunt is what? This is the bronchial vein. Bronchial vein contain which kind of blood? Venous blood. And this venous blood is draining at which level? The venous blood is drained at the level of this pulmonary vein. So, pulmonary vein contain pure oxygenated blood, and there is mixture of this venous blood with that of the pure oxygenated blood. So, this is nothing but your shunt. Getting my point? So, this is known as the physiological shunt. So, there is drop of partial pressure of oxygen even at the arterial blood. So, now if you look at the partial pressure of oxygen from the atmospheric air to the level of alveoli, then there will be drop of partial pressure of oxygen in a step by fashion. So that has been depicted in this picture. So initially, if you think of the dry air, what is the partial pressure of oxygen? 160 millimeter of mercury. That is the atmospheric partial pressure of oxygen. Then when this air is entering at the level of the lung, there is humidification, and because of the humidification, partial pressure of oxygen is dropping to 149. This is the PiO2, partial pressure of oxygen in the inspiratory air. There is further drop of partial pressure of oxygen in the alveolar region. So when it is entering at the level of alveolar region, the partial pressure of oxygen is 104 to 100 millimeter of mercury. So this is P capital AO2. Now when that oxygen is further reaching at the level of the arterial blood, there is further drop of the partial pressure of oxygen. So that is known as the PaO2. So this is P small AO2 is around 95 to 98 millimeter of mercury. Now this oxygen, when it is delivered at the level of tissue, the partial pressure of oxygen is very less. On an average, it is said that the tissue partial pressure of oxygen is on an average 23 millimeter of mercury, but it has a range of 5 to 40 millimeter of mercury. So because the tissue partial pressure of oxygen is very less, oxygen can easily diffuse from this arterial blood to the level of the tissue, because the tissue partial pressure of oxygen is very less. And when that tissue, after delivering the oxygen to the level of tissue, when it is reaching at the level of the venous blood, again the partial pressure of oxygen rises a little bit. So the venous blood partial pressure of oxygen is written as PVO2, is around 40 millimeter of mercury. So this step by step decrease in partial pressure of oxygen, is known as oxygen cascade. Getting my point? So this is all about your principles of gas exchange. So the bottom line is that we have learned how the oxygen and carbon dioxide transport happens in the lung, what is the formula to calculate the diffusion capacity of the lung, and then we have calculated the formula how to calculate the alveolar gas partial pressure of oxygen. Okay. Now if you look at the MCQ, most of the MCQ is based on calculation. So first MCQ, at an altitude of 1300 feet, okay, at an altitude of 1300 feet, the barometric pressure is 447 millimeter of mercury. So what is given in this question? The PB, barometric pressure, has been given as 447 millimeter of mercury, and they are asking you calculate the PiO2 of moisture. So obviously PiO2 means when the the atmospheric air is entering at the level of conducting zone, there will be moisturization. So what is the formula for calculation of the PiO2? I told you the PiO2 is calculated by this formula, Pb minus PH2O multiplied by FiO2, right? Now Pb is given here 447 millimeter of mercury. I told you PH2O is 47 millimeter of mercury irrespective of the altitude, and FiO2, that is a fraction of oxygen in the inspiratory gas, that is the percentage of oxygen. Remember, the percentage of oxygen is not going to change. The composition of the atmospheric air is not going to change whatever altitude you are ascending, right? So composition means the amount, the percentage of gas. If it is 21% oxygen here, the same 21% oxygen will be present even at the top of the Mount Everest, right? That is, composition is not going to change. Total pressure will drop and the partial pressure will also drop, but composition remains same. So I am going to multiply 21 upon 100, right? So this will be 400 multiplied by 21 upon 100. So this is very simple, 84 millimeter of mercury. So in this question, answer will be 84 millimeter of mercury. Okay. Look at the second question. So the second question, calculate the alveolar arterial oxygen gradient from the following information. So what we are going to calculate here? We are going to calculate what is the partial pressure of oxygen in the alveolar gas. Then you are going to calculate what is the partial pressure of oxygen in the arterial blood, and the difference between this is known as the gradient of partial pressure of oxygen between alveolar and arterial blood. Now if you look at the value, the P small aO2 is already given. So P small a is already given, that is 49. So you have to basically calculate what is this P capital AO2, and then only you are going to find out this alveolar arterial oxygen gradient. Okay. So two values has been given here, PaCO2 and respiratory quotient. Now, if PaCO2, arterial blood carbon dioxide, is given as 48 millimeter of mercury, we can assume that approximately P capital AO2 will also be 48 millimeter of mercury. Okay. So, P capital AO2 is given. So, now we are going to calculate the PaCO2, partial pressure of oxygen in the alveolar gas. So, the formula is Pb minus PH2O multiplied by FiO2. I hope you recall this formula. Then P capital ACO2 upon your RQ. So, this is the formula. So, now I am going to put the normal value of all of this because this has not been given in the question. So, Pb we are assuming 760 minus 49, okay, sorry, this is 47, FiO2 is 21 upon 100. So, basically this whole fraction will be 150 millimeter of mercury minus the value that has been given here is 48 is the partial pressure of carbon dioxide in the alveolar gas, and RQ has been given as 0.8. So, this whole fraction is 150 millimeter of mercury, that we know. So, 150 minus 48 upon 0.8. Okay. So, this will be 60 millimeter of mercury. So, 60 millimeter of mercury means this is 90 millimeter of mercury. So, now we got that the PaO2, that is the partial pressure of oxygen in the alveolar air, is 90 millimeter of mercury. Okay, 90 millimeter of mercury. So, here I am going to put 90 minus 49, that is nothing but your 41 millimeter of mercury. So, this 41 millimeter of mercury is the alveolar arterial oxygen gradient or alveolar arterial partial pressure difference. Got it? So, this way you have to calculate the mathematical question. Thank you so much.